All right. So how you guys doing today?
Good.
Perfect. All right. All right. So we can move on to the chapter 2 again since last Friday. So we talked about the isotopes, right? Isotopes. So isotopes just simply saying chemical elements. But with the just different atomic mass number, meaning different numbers of neutrons, because the same chemical element means actually the same numbers of proton anyway. So only difference you can make in the atomic mass number will be only the neutron. If you have even though like carbon, or have a carbon 12, carbon 13, they'll still have a same number of proton, which is 6, but they have a different numbers of neutron. That makes different number for atomic mass number for the isotopes of carbon, hydrogen, nitrogen, so forth. Okay. So this is what I learned. We learned how to calculate for the natural abundance of each different the chemical the isotopes of same chemical elements. There are a couple of things I need to mention more. If that is the case, this is where you can put the numbers. So if you put the chemical element symbol in here, this letter X, maybe you can put the carbon here. Okay. If you want to put the carbon 12, which is normal, most abundant carbon in the universe, this is where you can put the atomic number, which is your number of proton over here, which can be found easily on the periodic table. If you look at the carbon, it says right under number 6. Its atomic number is ID. Okay. And you guys already saw this many times in the previous Friday lecture. This is where I put the atomic mass number. So this is proton plus neutron. So for carbon 12, it's going to be 12, because it also has 6 neutron over there. And then I want to talk about this one over here. This is where you can put your formal charge. So formal charge can be only defined or determined by numbers of electrons. So as you know, when we look at the atomic structure, it has a nucleus at the center. Okay? It's made of proton plus neutron, an electron on the outer shell, so they can move in the certain space. So as you know, electrons is negatively charged, and the proton is positively charged, and overall it become neutral. Okay? So if this atom wants to be neutral, meaning, for example, if this one has maybe 10 electrons on this atom, it should also have 10 proton. Okay? So it can be fully in sum neutral. So it would be zero charge. So if it's neutral, you can put just 0 on the top right corner of your chemical symbol, which is carbon or nitrogen and so forth. So you can tell. So if you say there's 0 number here, you're actually indicating there are also 6 electrons as well. Because the formal charge only tells you the relative comparison between numbers of electrons and also the protons. So if this is a 0, means they have equal numbers of electrons and also the protons, either negative and positively charged. So in sum, they give a 0 number for formal charge. Okay. So what if it has 7 instead of 6? Okay. So let's assume this carbon has, instead of 6, maybe it has 7. So it has 1 more of the electrons than the numbers of protons now. So meaning, if this carbon will carry the additional 1 more electron on here, then it will become -1. So the formal charge of the carbon with the 7 electron will become -1. And this is the way you can put the formal charge on your chemical element symbol. Makes sense, right? Perfect. So If that is the case, we do this because the electron has the negative charge. But if we assume if there's only 5 electrons instead, now I change the 7 to the 5. So you actually have one less numbers of electron than the ones of like protons now. So that will make this one missing one electron from the neutral form of the carbon. So if you're losing a negative charge, is same as what? You have one positive charge. So in that case, it's going to be 1 plus, as it's a formal charge of the carbon. Makes sense, right? Does it make sense? Good? Perfect. So if that is the case, I'll give you one practical problem you may see on the exam here. So could you guys find the nitrogen on the periodic table? It's right next to carbon, right? Do you see what number on the top right corner on nitrogen block? 7, right? Okay, perfect. So if you have nitrogen, it has how many protons now then? If it's a 7, there has to be 7 protons, right? So there's the 7 protons over here. And then you can also see the numbers below the chemical symbol. If you have a good eye, I don't know if it's about 14, right? Does it say 14? Could you guys double check with me?
Yeah,
It's 14?
Really close to 14.
Perfect, thank you so much. So you can do 14 over here, okay? That's good now. And now, let's say I put 1 plus over here, okay? And maybe I can ask you numbers of electron in this nitrogen cation. So you have this is atomic number 7, so it should have 7 protons, but it's positively charged, meaning it has one additional plus charge. Then it should have only 6 electrons. So you can add 1 plus charge. Okay. So if that was the negative, then now there are 8 electrons there. Make sense, right? We're good? Perfect. You guys doing so great so far. So how about this one instead? So if you look at the maybe oxygen, okay? If you look at the oxygen over here, and then you can look at the atomic number, which is 8. And if you look at the periodic table very closely, the numbers in the below is smaller than top, but it's close to 16, right? Okay. But that is the case, then I'm gonna say it's a negative charge there. Okay. I put the negative charge on this oxygen here. Could you guys maybe, I'll give you 1 or 2 minutes. Could you guys tell me the numbers of protons and neutrons and electrons? 3 of them all together. Yeah, go ahead, just to try by yourself, just 1 minute. So you have an oxygen that has 8 as its atomic number, and the atomic mass number is the 16. And it's now have a 1 negative charge. So what can you say about the numbers of protons and neutrons and electrons? That's the question. I will start with the numbers of protons and the mass, atomic mass number, and then the numbers of electrons at the end. Okay, so what might be the numbers of proton here? Anyone?
8.
Perfect. Okay, so but the atomic number is the what? Numbers of proton plus numbers of the neutron. So 16 minus 8 will be 8. Perfect. But it has 8 protons, but it has a 1 negative charge. So the numbers of electrons should be bigger or smaller than numbers of protons? Bigger. So it will be 9. Perfect. That's it. Okay. That's all you need to know. So if you can have a subatomic particles, numbers of them, by just looking at where your chemical elements are located in the periodic table, and looking at the atomic mass number on the top, and if you can find where the formal charge is for that element, the atom or the molecule, you have a lot of more information about just doing a bit of a one simple calculation. Makes sense, right? I think we're good here, so I'll just move on. But if you have any other questions, just let me know. Okay. All right. Okay. So we just talked about the formal charge, atomic mass number, atomic number, everything. So if that has something chemicals has a plus or negative charge, and we have the one that is the charge, formal charge, we call them ion. Ion. So if it is atom or molecule, doesn't matter. If that has a certain formal charge and that structure, we're gonna say this ion. But when it's positively charged, we're gonna call that cation. Okay, we're gonna call it cation. If it's negatively charged, we're gonna call that anion. Okay, so just cation and anion. This is what we're gonna do for this one. So once again, anything that has a formal charge or with a plus and minus, we can call that ion. But it's positive, you can more specific on that certain type of ion, that's cation. If it's the negative charge, you can call it anion. So you can actually have more information on the name of the elements or compounds, indicating if it's positively charged or negatively charged. So this is kind of important because later on we're gonna learn about some octet rule that you can find the trends in the periodic table. So one brief thing, if you look at the periodic table, okay, so someone looks like this one. Okay, so if you look at this one over here, then some here, you don't have to know a specific number, but you see there's the silicon, SN, and all the SNP elements are where you can find some metalloids. But this is a kind of trick one, so you don't have to know them for now. I'll indicate it more specifically at the later time. But most important thing is up to this part, like staircase wise of here. This is where you can find the metal. Okay, so if you look at the periodic table, most part of your periodic table elements are metal in metallic form, and there's some in between. There's only few are we call metalloids. Okay, meaning it is semi-metal, semi-non-metal, and those are the ones that is non-metal. So non-metal means they're not making metallic bonds. So they will show you different physical property of the one that is metal, non-metal, or between is literally somewhere between, like a pseudo-metal, pseudo-non-metal. This is why sometimes you see the silicon a lot for the microtube, which is a semiconductor. Anyway, so if that is the case, only thing that I kind of want you to know that the ones in the metal will tend to be cation, because they are each to carry the electron through themselves. So they tend to lose electrons, so they can be more stabilized. This is common for the metal, but the one that is the non-metal is the one actually going to get the electron, except the last column, which is no gas. They don't usually do anything on chemical reactions, but except the last one. Those are the one on the right will tend to have a more electron, so they can have an ion form. But cation wise, it's more case for the metals on here. So I'm kind of telling you this because there's a certain ways we can actually make some name for the compound. But so far it makes sense, right? So one that on the left on your periodic table is the one that is going to be cation most of the time. The one on the right side, which is most of the non-metal, except the last column, which is noble gas. We're gonna cover that soon later. month, but that is going to be most likely an anion. It's because of the octet rule that we're gonna find in those noble gas column that we're gonna talk when we hit the electric configuration form. I think maybe end of this month or early next month. But anyway, for now, I just want you to know the ones on the left will tend to be cation. The on the right, except the last one will be the anion. Okay. So, and the metals are here, no metals there, somewhere between the metals. So if that is the something that we can find out, at least briefly from the, just looking at the periodic table, you can actually use this one in the certain type of nomenclature of the compounds. Okay, so the maybe most common compound you can name it is the one with the metal cation plus non-metal anion. Okay, so in this case, there's a certain things I need to tell you. So if you look at the sodium, and if you look at the chlorine, so if you look at the sodium over there, it's in the first column. It's third row in the first column. That's where you can find the Na, the sodium over there. And the chlorine is right next to the last column on the right side of the periodic table. So you don't have to worry about the one in the kind of in the middle block at the bottom in the periodic table, but you can skip that one. And we normally gonna categorize each column of the periodic table by just counting 1, 2, 3, 4, 5, 6, 7, 8. Okay. Once again. Okay. So here's the thing. So if you look at the carbon there, for example, carbon is right there. It's group 4. Okay. So if it's a nitrogen, this nitrogen is a group 5. I'm sorry. And then this is a group 6, and the fluorine will be group 7, and the one on the last one, if you see the neon, this is the noble gas over here. So this is where you can find each element in the different column. We call this a group. So if it's in the first column, we're gonna call the elements all in the first column group 1 elements, and second group 2, skipping this D block and the down low, and you start from the 3 again here. It'll be group 3, 4, 5, and 6, and 8 over here. Okay. So if that is the case, only thing that I want you to know for the metal wise, if that is in the first column, if you look at the periodic table, there tend to be cation, right? Once again, there will be metal. And then if it's group 1, you can say it's become 1 positively charged. Okay? So that means if you look at the magnesium, it's right next to sodium in the periodic table, that is going to be 2 plus, because it's in group 2. Okay? So if you look at the aluminum, which is in the third column, is going to be plus 3 in ionic form. Okay? And then when you get to the number 4, they don't do it anymore. Okay? So they don't do it anymore in number 4. And here, they're going to, from the last column, it's noble gas, you're gonna do -1, -2, -3. Okay. Okay? So this is once again 1 plus, 2 plus, 3 plus, nothing, -3, -2, -1, nothing. Okay? Because of the noble gas octet rule, I'm gonna tell you a lot more detail when we hit the electric configuration form later. But for now, I just want you to know, once again, sodium is the metal. Because in the left side in the periodic table, that means it's going to be cation. That means it's going to be positively charged ion. When it's dissolved in water and some ionization happens. But it's group 1, so charge of that positive charge on the ion will be just 1, because it's in group 1. Okay, that's why its mechanism is 2. So how about calcium? the calcium is in group 2. So when it ionizes in water, what plus charge it would have? The calcium. Plus 2. Perfect. There you go. That's it. That's all you need to know, right? This is all that says over there. So that's good. So if that is the case, we know by just doing the simple rule on the periodic table, we know this is going to be plus 1 charge, and this is a negative 1 charge in ionic form when it becomes an ion, ionized, okay? So, if that is the case, because of the Coulomb's law, we kind of already know this as common sense. We just experience the daily life every day, you know, in our life, that the plus, something that's plus, something that is negative charge, they attract each other, okay? So they're going to have interaction between these two. But as you can see, this is the ion, this is cation, this is an anion, and we're gonna call this is interaction between two ions, so we're gonna call this ionic compound. And then here's the thing: whenever you try to name this ionic compounds, only thing that you need to know is very simple. This might be the simplest nomenclature you can do among all the chemical compounds. That you see the NaCl-, and whenever you try to name it, you always name the one on the left first. Meaning, so if you have a sodium and chlorine, you look at where they are, okay? And the sodium is more on the left side of the periodic table than chlorine. Then you're always going to start naming with the one on the left. So you're not gonna name it like a chlorine, sodium. You're always going to name it in the left to the right in the periodic table column, okay? So that would be either sodium, chlorine. So let's try to do this. So whenever you have a NaCl ionic compounds, what I'm gonna do is the sodium, okay, and chlorine. Just write it in the way it says in the chemical formula. So we're gonna, this is what we call chemical formula. Okay, so once again, always left to the right in the periodic table. And sodium, this is chlorine. Okay, this is chlorine. But whenever you have the anion part of your name in the ionic compound, you try to get rid of that last Ne and put it De. That's it. So if that is right, that is the metal. So you have a metal cation, non-metal anion, bound to each other as an ion form. It makes ionic compounds. And when you try to name it, you always go from the left to the right. And for your cation part name, just copy and paste it from the periodic table. That's all. Sodium, it says, just copy the sodium. But the second part of your anion part name of your ionic compound's name, just change the last as IDE. Okay, so that makes sodium chlorine now, sodium chloride. That's why we call this sodium chloride. Okay, makes sense, right? Does it make sense? We good? Perfect. Okay. So if that is the case, let me give you another one. Okay, I changed this one to magnesium. Okay, magnesium. So magnesium is in group 2. Okay, so here's the thing. The first thing you need to change is it's a formal charge. Now it's not in the group 1, but it's group 2. Meaning you can find it in the second column of your periodic table. So this is actually going to be not just 1 plus, but it's 2 plus. Okay, so in this case. You can also try to make ionic compounds because this is also metal. This is non-metal. So when it's ionized, they're going to make some ionic compounds. But the problem is, the formal charge doesn't add up. It's like before we had a sodium chloride, it was pretty nice and clean and simple because there's a +1, -1. There's equal charge, can attract each other, makes no change in the numbers of the chemical formula form. But now it has plus 2 is negative 1. So when you write the chemical formula for those compound, we're going to write it in MgCl2, not 1. Because it has a 2 plus charge, but you know each chlorine anion will carry only negative charge, one negative charge. So if you want to have a neutral ionic compound, you know there has to be 2 chlorine anion interacting with 1 magnesium cation. Because it has plus 2 charge, it only has negative 1. So in chemical formula, you have to write magnesium chloride. But in the chemical formula, you have to put MgCl2, not 1. Make sense, right? Okay, good. All right, so make it even worse. See, if this is this case, okay? If you have aluminum instead now, if you find the aluminum over there, it's on the third column, okay? So now it makes 3 plus. So in this case, only thing you need to do, just change this aluminum and aluminum chloride, but it's not 2, but it's what number? 3. Perfect. So in this case, this is a very good ionic compound naming. Is quite simple and easy because the only thing you have to worry about is the chemical formula. But when you name it, you don't have to do it. Meaning, it is still aluminum chloride. That's it. Even though there's 1 or 2 or 3, you don't have to worry about it because you know the formal charge of the metal and non-metal. Just applying the simple rule that we just did on the periodic table. If it's in the third column away from the noble gas, it's -3, 2, -2, -1. From the right, from the left is +1, 2, 3, 4, 4. I'm sorry, 3 and 4. Okay. So this is how we can name the ionic compounds. Okay, because we know by just looking at where the elements are in the periodic table, we automatically know the formal charge. So even though we name it in the just cation name and just anion name plus IDE, it's still going to be tell you how many of each will be there as a chemical formula anyway. You don't have to tell me. If I call this aluminum chloride, I know there will be 3 anyway because I know what charge it will carry in each element. Okay. So let's try to do this one. First of all, am I writing the chemical formula first? So sodium is in what? First column right there, so +1. Bromine is where? It's 1 column away from the last column on the right, right? So that is -1. This is +1. So in chemical formula wise, it's already perfect. NaBr, right? Okay? And whenever you name it, right? Whenever you name it, it's just the same, sodium. Okay, once again, you don't do bromine sodium, right? You always go from left to the right on the periodic table, where the top and bottom doesn't matter, just left to the right. And this is bromine, right? And then you're just going to change that last part of your anion name is ID, so now you can have the name for it, it's a sodium bromide, okay? It's all the same. It's fluoride, chloride, bromide, oxide, and sulfide, all the same, okay? See, this is for how we're gonna name the ionic compounds. Only thing that we need to be careful with is the chemical formula, because you may wanna know how many of each cation and anion will make the covalent bonds to be neutral compounds. Okay, okay, so makes sense, right? Good. Okay, so let's move on to slightly bit more complicated. Slightly bit more complicated. It's much the same though. Okay, not so much. Okay, so if you think about N2O5, okay, N2O5. So meaning there are 2 nitrogen, there are 5 oxygen, but unlike the ionic compound we just discussed, nitrogen and oxygen are both non-metal. It's not about the metal cation, non-metal interacting in the ionic bonds, but now they're just all non-metal, just making simply chemical bond to each other, right? So in that case, the problem is, if we just say, like you did for the ionic compound, if I just say nitrogen, same, this is the oxygen, right? But we put the ID, so it'll be oxide. Okay? We just put ID on the anion part. So you always, this is the same. You always put the nitrogen first because in the left to the oxygen, right? So anyway, so if this is nitrogen oxide, if I say this, nobody will know how many nitrogen, how many oxygen are making bond each other, right? Because the ionic compound, you don't have to, because you already know which element will carry what form of charge. If it's neutral, we know how many of that will be combining each other. But this one we have no clue, because they're not doing ionic bond, they do covalent bond, or the chemical bond they're doing each other. So in that case, only difference you need to make from the previous one is you have to number each ones. You have to number the nitrogen, you have to number the oxygen too. So what you can do is, if there's a 2, if you guys know, I don't know if it's the di. Di means 2. So mono means 1, di means 2, tri means 3, tetra means 4, 5 is like a pent. So what you can do is this is the di nitrogen pentaoxide. Okay, so this is pentoxide, okay, or pentoxide. I think they're pretty much the same. Okay? Pentoxide, okay, or pentoxide. So only difference, we call this. So this is not ionic. So we had. Molecular compounds, because this is not about the ionic bonds, but they made it in the non-metal bonds. So we're gonna call this type of compounds molecular compounds. In this case, because we don't know how many of each are there, so we're gonna use either the numbers of each nitrogen and oxygen. But we also do the ID for this one as well. But the also additionally for numbering each element in the compound is necessary here. It wasn't necessary in the ionic compounds because you didn't have to, because we know the formal charge, we can assume how many for each compound anyway. For this one, it's kind of hard to do the same way. Okay? So if I change this one to this one, okay? I just made it up. I don't know if it. Anyway, if that is the thing, only thing you have to do is once again the cation part, not cation. I'm sorry, the left element part of the nomenclature is always easy. So if you look at the P, it's right in over there. Okay, you see there's the P in the group 5, the fifth column. So this is phosphorus here. So, but you just can say phosphorus, right? You need to do what? Triphosphorus. Tri. So this name will be triphosphorus pentoxide. Does it make sense? You good? Okay, perfect. All right. So the major difference between ionic compounds and molecular compound is it is becoming from metal, non-metal, or it's non-metal and non-metal. Okay, that's the only thing you have to know. And if it's non-metal, make sure you also number them on each element. But ionic compound-wise, you don't have to do. Probably before the exam, I'll give you more particular example problems, so we have a better idea. But let's move on to the next one, so we can have a somewhat good brief idea at least. But how are you going to name this compounds and various compounds? So the next one is what we call binary acid. Okay? So this one is the one that show you. Let me start with what this acid and base means. Okay? Acid and base. Before we try to name this one, let's try to make sure that what it really means by acid and base. Okay, so acid is the one that donates hydrogen cation, because this is a hydrogen, but it's positive charge cation anion, or you can say it's a proton. Okay? because the hydrogen is just the 1, meaning it has only one proton and one atomic number. So this simply one proton at the center, one electron moving around. But if you remove the electron from the hydrogen, it's just simply same as one proton right there, because it's so small. Okay, so you can say the acid is the one that donates the hydrogen cation or donates the proton, meaning the same thing. Okay, the base is it donates the OH minus. Okay, this is kind of a hydroxide anion. This is what we call. This is negatively charged, or you can say it upsets. It does donate, but it actually steals the hydrogen cation, the proton. You can say it's the same thing because the I'm going to tell you more in detail later. But if you're losing the something that is negative, it's the same as you getting the positive, right? So either base will donate the OH minus or accept the protons, or do the opposite job that exit does, which is they donate a lot of the H plus. Okay, so I'll give you an example here. Let me give you some example here. So if you look at the HCl, do you guys know what this is? This is very strong acidic molecule compound. So this is very strong because when it goes into the water, it becomes ionized. So meaning they're going to break apart as two ion form, which is cation and anion. So meaning when this goes into the aqueous medium, they're going to break apart into two ions, cation and anion. And the one of the cation part is what? Your hydrogen cation. So this is a really good example of acid, HCl, right? Because it does give you this one in the chemical and the aqueous conditions. So if that is true, we can define this compound as acid, because we'll eventually have a lot of potential to give us a lot of numbers of H plus hydrogen cation or proton in that way. So, but this is kind of funny because it only has 1 and 2. So 1 and 2 hydrogen and the elements 2. So this is why we call this not just acid, but binary acid. It's like a binary, like a 1, 2, 1, 2, 1, 2. So another example would be, you can have a HBr, SF, and so on. So you have just a pair of hydrogen, anion part, the elements 1, 2, 1, 2, 1, 2, 1, 2. In that case, we can call them. They're all acid, but binary acid more specifically, because it's just 1, 2, 1, 2, 1, 2. So if you have a certain type of acid that is in this form, what you can do with naming those types of a compound is for hydrogen, you just need to say hydro something. So because it's a binary. And this is the same, because you're always going to name the ones on the left on your chemical formula first. So this is a hydro something. And same here, this is chlorine, right? So just copy chlorine there. Okay. And then only thing you have to change now is this hydrogen, I change it to the hydro, right? And now chlorine, I just copy the same. But when you see this, the Ni again, we're gonna change this one to, again, but not IDE, but to IC acid. So, for binary acid, only thing you have to know is you change the hydrogen part of your acid compound to the hydro, and copy the other later chemical element same, but at the end not IDE. It will be at this time IC acid here. So the full name of the HCl will be hydrochloric acid, and which is a very strong acidic solution. Okay, so can you guys actually do this one? This is HBr. So this is the bromine, but you're gonna change the last part of the bromine as IC acid here, and this will become not hydrogen but hydro. So will become hydrobromic acid. Perfect. Okay. How about fluorine here? This will become hydrofluoric acid. That's it. And You have iodine too. It will be hydroiodic acid. Okay, it's easy, right? That's all you need to know. Okay, if it's binary 1 2 1 2 1 2, that's all you need to know. Okay, does it make sense? Good. Okay, perfect. Okay, so if that is the case, we have a bit more complicated the acid compound. One of them is this one. So this is HNO3. This is more complicated because this is not binary. You have a hydrogen over here, but the other part is not just one element, but the complex. So this is a polyatomic anion, because whenever it goes into the water, they also donate the protons there, but this whole thing, not just one element, become an anion. So normally they carry the oxygen in it when it form the polyatomic anion. So some people call this oxygenic anion, but normally in general we can call this polyatomic because there are more numbers of atoms than one. Polyatomic anion because it's negative charge and positive charge. And then I'm going to talk about how you're going to name this one. This is I think this might be the most typical part of the nomenclature. But we'll cover this one later. The answer is nitric acid, but I'll tell you why. Okay, this Friday. Okay, so I'll stop here. So let's have some time for the extra credit